Cool. All right. Good morning, good afternoon, wherever you are in the world. I'm very happy to introduce you to Victor Ramirez Delgado. I'm proud of my pronunciation.
Thank you.
He is visiting us from University of Delaware, and we met in DC 2 months ago we were in an exoplanet conference at the Goddard Space Flight Center, and I thought it would be a great opportunity for him to visit us and talk about his research. And he's going to talk about his PhD work on radial velocity. So take away.
Thank you so much. Thank you everyone for being here, and thank you so much for the invitation to be here. I am really, really thankful, and it's been a really good time to be here. Give me a sec to make sure that everything is working. Okay. So yeah, so thank you very much for the introduction. My name is Victor Ramirez Delgado. I am a PhD candidate at the University of Delaware and also a visiting student at Argonne National Lab. And today I'll be presenting you my work on disentangling cellular activity in rare velocity planet searches. First, I'll start with a little bit of the background as to planet searches and how those studies entail with rare velocities. So the quest for finding habitable worlds we can date it back to around 1995 with the discovery of the first exoplanet around a sun-like star, 51 Pegasi b. Fast forward to the current day, and we have hit the milestone where we have exceeded the discovery of exoplanets of 5,500 exoplanets to this day. In order to get to this point, we have to do a lot of work in terms of the techniques to detect exoplanets. So a lot of development, for example, for radial velocities, that was possible to detect 51 Pegasi b to radial velocities back in 1995. As well as the development of the transit method, direct imaging, which is of particular interest here at Gemini, microlensing, and astrometry, which will hopefully become one of the main sources or main techniques to detect exoplanets in the next few years. Do we also have to take into account all of the work that has been going in terms of mission and space-based missions that went into detecting, and now we can even characterize the atmospheres of these exoplanets. Just to mention a few of them, we have Spitzer, CoRoT, Kepler, TESS, and now we have JWST. And the future looks bright in terms of the field of what we're going to find in the next few years, in the next few decades. First of all, we expect that the number of detected exoplanets is just going to keep increasing with future missions. I mentioned a little bit of astrometry. We expect that Gaia, DR4, will allow us to detect another thousands of exoplanets, and hopefully at long period planets. We also expect that the Roman Space Telescope will give us even more detections thanks to the use of microlensing. And this image that you see on the slides, it shows the number of detection of exoplanets as a function of time, as we can observe how when it suffered a great increase as we go from the 2000s in the 2010s until now. And we can just expect this curve, this trend to just keep increasing as we go over time. And when we look now at the long term, what is the goal in terms of like the next few decades, in the next 20 years? And that we're talking about the Habitable Worlds Observatory, HWO, which is the next NASA flagship mission that is designed to directly image approximately 25 exoplanets to search for biosignatures. The NASA Exoplanet Exploration Program is already preparing for this new mission and has already published a list of 164 possible targets for HWO. Now, what will be the role of rare velocities on this context on the next few years? Well, it turns out that rare velocities is the most favorable method to detect an Earth analogs around sun-like stars. The reason for this is because rare velocities allows us to probe a lot of the orbits and masses that we can find that we might not be able to probe with transits or direct imaging or astrometry. And in particular, we're very interested in looking for Earth analogs, where we not only are looking for planets that have Earth masses, but are also around a sun-like star and at a period of approximately 1 year. The other thing what's important is because with rare velocity, we can use them for mass determination to determine the masses for the targets for HWO. with the masses, we'll also have more information and a priority, so that when we point our telescopes towards these missions, we'll be hoping that it will be for planets that look somewhat like they have the same condition as Earth. And then also the other possibility is that a lot of the possible targets for HWO are radial velocity only systems. So these planets have only been detected to radial velocities. So now I'll jump into a little bit of what is the principles of radial velocities. And to get a little bit of an idea, we have our system where we have our star and our planet. The gravitational attraction between these two bodies causes them to orbit a common center of mass. And we can measure this motion that the planet induces on the star by looking at the spectral lines and see how, as the star moves towards us and away from us from our point of view, the spectral lines get blue shifted and red shifted because of the Doppler effect. And ultimately, what we're left with is a time series that shows us the oscillations of the star as it moves over time. From this time series, we can infer several parameters from the period, from the orbit of the planet, excuse me. So for example, if we looked at how long it takes from one oscillation to repeat, we can extract the period, the orbital period of the planet. If we looked at how big is the curve, we can extract the semi-amplitude, which tells us about the mass of the planet. But ultimately, we need more than just the period and the semi-amplitude to describe the orbit. We also need to determine the eccentricity of the orbit, which can tell us how elliptical the orbit looks like. And then we also need the time periastron passage and argument of periastron, which tells us a little bit more of, for example, we can think of like the phases. And this image shows really well what happens when you have a radial velocity curve and how the eccentricity changes as you go towards the left, or I guess right, on the screen. And you can see that the curve for the radial velocity becomes sharper as you have a more eccentric orbit. Well, for the cases if you go down and you increase the argument periastron, you can see that there's kind of a little of a shift on the orbit, except for the case that you have a circular orbit when you have an eccentricity of 0, where we simply just have, we don't have these changes because of having a perfect circular. Now, using these parameters, then we're able to determine the minimum mass, what's called the minimum mass. The minimum mass is the mass of the planet times sine I, where I is the inclination of the orbit. So in this case, the only unknown that we're left with is inclination of the orbit with respect to our point of view. And while we cannot determine that to radial velocities alone, it is possible to determine. And even if we the minimum mass, we're still able to get an estimate of the masses for planets that we detect. Now, one of the major things that we have to worry about in the case of the future for radial velocities is what are main sources of noise, what are our main sources of errors. As many astronomical sciences, we have to deal with photon noise and we have to deal with instrumental noise, which have to do a lot with the telescope, the characteristics of the telescope, the aperture, the cadence. But one of the major sources of noise that now we have to really consider, in particularly when we get to more and more precise radial velocity, to the point that we have extreme precision radial velocities, is the noise that comes from the star. The noise that comes from the star, it's intrinsic to its surface. So there's a lot of variability that happens at the surface, and this induces, it's kind of like a noise floor that we have to understand in order to be able to find planets like Earth, because planets like Earth only induce a radial velocity amplitude of approximately 10 centimeters per second, while these signals or this variability that happens at the surface of stars induces variability on the radial velocities that is on the order of meters per second. So a lot of the effort currently in the radial velocity community is to try to understand, like, how do we explain stellar activity and how can we correct for it in the radial velocities. To illustrate a little bit of stellar activity, the best example is to look at our favorite star, our sun. This is some animation from the Solar Dynamics Observatory that show the sun at solar minimum and at solar maximum, where we can see that at solar maximum, there's a lot going on at the surface. We have a lot of sunspots on the surface, but even at solar minimum, there's still a lot of physical processes that happen on the surface of the sun. The surface of stars are simply filled with physical processes, from magnetic fields, motion of convective plasma that goes in and out or that goes up and down. And we have to, first of all, try to know what we're dealing with. So in the types of stellar activity, the first one that I'll talk about is the stellar cycles, which is related, or it's what I showed before. The sun goes through this 11-year cycle where it goes to a maximum that we have a lot of sunspots. Then it goes to a solar minimum where you don't have as many sunspots, and it just keeps repeating this behavior. This is also observed for stars, for many other stars that we have gathered data for them. So we expect this, and we observe this in many other cases that we look for planets. And these variations can cause a variability in the velocities on the order of 10 to 20 meters per second. So it is a significant source of noise. We also have to worry about star spots, because star spots give you also a signal about the rotation of the star, and they can also change the shape of your spectral lines. So in particularly, the rotation of the star can also kind of look like a periodic signal in your rare velocity data. And that can be problematic because when you're looking for a periodic signal, you might think that it's a planet, but it might actually be the rotation of the star. And this motion or this process also cause variations on the order of meters per second. We also have to worry about oscillations, for example, pressure modes, P modes, that happen because of the acoustic waves inside the stars. And then lastly, granulation, which even in the quiet stars, even when we have a solar minimum, granulation will always be present. The motion of the convective, or the motion of plasma as it goes up and down in these convective cells, it's always going to be there, no matter if we are looking at a quiet star or not. And even this motion can induce variations in rare velocities with amplitudes of meters per second. Okay, with that in mind, now we talked about how do we go about hunting for planets? How do we find these planets? To understand that, we have to first have an idea of what a rare velocity time series looks like. We can think of, in the first order approximation, that rare velocity time series is composed of a planet signals, plus stellar activity. Now, as many ground-based observations, we also have to consider a few more things. So this is an example time series from the paper from Botterill in 2016 for the storage AC164922. For this case, we see that in some cases, we have a lot of observations that are closely spaced with each other over time. So they're taking in between them in maybe just a matter of like few days. There's some other sections where there's very scattered time. We have a lot of minimally spaced sampling. So observations that we're taking just maybe every week or every month or so. And this causes the observations that we have to deal with to be very unevenly spaced. And this will prove particularly hard eventually when we use the methods of how do we find the periodicities. So how do we go about finding signals in this data? Well, to go ahead and find signals in this data, we have to use our Fourier methods. In particular, in astronomy, one of the most common methods that has been used is a long-scale periodogram, which is equivalent to doing a least square fitting of a sinusoidal model at each frequency. So the best way to show it is to illustrate it with a figure. In the top, you see what it is, a time series, a generated time series where it has the black line is just what we think is the original signal, the true signal. And our data points that are with the dots, they show what the signal will look like with some white noise, where the white noise could be coming from stellar activity or instrumental noise. And when we take the periodogram, what we expect is to look at the periodogram and find a peak at the right frequency where we see a periodic motion. So for example, in the case of this generated data, we know that there's a sinusoid that has a frequency at 0.05. Now, another important question that arises, or another important factor of the periodogram that we have to worry about, is the resolution of the periodogram, which tells us how small is the separation between frequencies to be able to resolve them, which is also an idea that it's kind of sharing optics. We know that if we have two sources of light that are too close together, they're just going to blend with each other. And we cannot tell the difference if we're looking at two sources of light or just one. The reason why I point this out and why it's particularly important it's to illustrate it also with an example, which is the case of Corot 7. For the case of this star, back in 2010, there was a detection of a planet at approximately 9 days, which is planet D. Later on, Hayward et al. In 2014 detected or reported that this planet detection was a false positive because the period of the planet that is illustrated here landed really close to one of the harmonics of the rotation period. So Hayward argued that the signal that was reported as a planet before, it wasn't actually a planet, but actually one of the harmonics of the rotation period. And this is just an illustration as to why is it important that we have a limited resolution. The resolution is only given by how long your time series lasts. So I apologize for that. I should have mentioned that in the previous one. This equation, the resolution, shows that the resolution is given by 1 over the total time baseline, where the total time baseline just shows you how long is your time series. If you have a time series of 100 days, that means that your resolution is 1 over 100 days. So going back to this case, this is particularly important in this case because sometimes you're going to have signals that are very close to each other, that you can have a planet period that might be close to a rotation period or a rotational harmonic. And for the case of Corot D, it is still, the existence of planet D is still contested. So the results of Hayward all kind of put into question the existence of planet D, but there's been some development from a paper in 2022 that claims that planet D it is real. So yeah, so this is another example of why is it important that we have to worry about the periodograms, because this is our first step. When we look for planets, the first thing that we normally do is to look at a periodogram to be able to find periodic signals. This is a question that is not only particularly important for variable velocities, but also for astroseismology and in the study of variable stars, because in particular, you want to be able to find frequencies that are close to each other. And there's been previous studies in astronomy that determine that you need a separation in frequencies to be approximately 1.5 times the frequency resolution to 1.44 times the frequency resolution to be able to determine if two frequencies are independent from each other. This example from the Kovacs 1981 paper, just the case where you have a data with two periodic signals in it, and you take the periodogram and you look at what you obtain, at the peaks that you obtain. For the case that you are in the bottom, you only have a separation of 0.9 times the resolution in between them. So you have a blending. You only see a single peak instead of seeing two different peaks. And as you separate them, as you go from a separation of 1.1 to 1.31, you start to see now the peak of the second periodicity. But here comes the issue that it is a problem that if you have closely spaced frequencies, then you're simply limited by the resolution of the periodogram, by the resolution of how long is your time series. The other major source of noise in the periodogram, in the frequency domain, is what's called the window functions, which is related to how the observations are sampled. So in this case, we can imagine that we have a signal. We have a signal that for this case is an example from the Van der Plas 2018 paper that shows our signal via a Gaussian function. The Fourier transform of a Gaussian function, which is simply another Gaussian function. But what you see at the bottom, this is our window function. It's a Dirac comb, which tells you just basically at a certain point you have a delta function. And these points are going to be our observations. Our observations are these Dirac functions. And when you end up with the data that we obtain is simply a multiplication of the signal, your true physical process multiplied by your observations, by your window function. So you end up with something that has kind of the shape of a Gaussian functions, but this Dirac delta function. And when you take the Fourier transform of that, you see that now your periodogram is filled with spurious peaks, where these spurious peaks are only caused by how unevenly spaced the observations are in time. So these spurious peaks can also appear to be real signals, but they're simply embedded just because of the way the observations were taken. And that's unfortunately something that we also have to manage because we are subject to weather. We're subject to the fact that there's sometimes that there's no time available to observe certain targets. And it's really hard to just get evenly spaced cadence for variable velocity observations. This is some of the work that I worked for a paper that was submitted a few months ago. So that explores this idea where on the left, you have a time series on that it's simulated with just a single periodic signal in it. The top one will be the true time series where we have a sinusoidal with some white noise. At the bottom, you have the same time series, but now we remove some of the observations to kind of appear that it's a variable velocity time series, where you have some parts where you have high cadence, some parts that you have some gaps in between the data. And then we want to see what happens when you look at the periodograms of these two cases that we know exactly what the ground truth is. What you find is that for the original case, we find the periodogram peak exactly at what we expect at the right frequency. But for the other case, what we see is that we actually find another peak very close to the true frequency that is completely spurious. And that is not only a problem because these horizontal lines, they show what is called the false alarm probability thresholds, which tells you out of these periodogram peaks that go above these lines, what's the probability that this peak it's completely spurious, that it can just because of random variations of the sampling or the error. And this peak that appears is also significant above the 0.1% threshold, telling us that in the case that we follow this statistical method to determine if it's real or not, then it will tell us that this is a real signal, but it is completely caused by just how unevenly spaced the observations are. So that poses also another big problem that we have to consider. But the reason why I highlighted this gray band area on the periodogram is so that you can see how closely spaced they are from each other. In this case, they are close if they're spaced less than twice the frequency resolution. So in this case, we can argue that because they're so close with each other, they might not be independent from one another. The other example that I want to highlight is that how it's important of the time baseline, the time baseline that determines your resolution. So for this example, I generated 3 time series. 2 of them were just sinusoids with their independent frequencies. And then the last one is the addition of the 2 of them. And what you obtain when you look at basically the evolution over time, which kind of simulates that if you take more and more data, you see that the periodogram kind of changes shape, but you do not find the right frequency until you have enough coverage of your signal, which is kind of what we expect. So for the case of the darker blue one, which is the addition of the 2 of them, if you don't have enough coverage, the periodogram ends up finding the wrong frequency up until you have a resolution of, or until you get to the point that the frequency is separated from the 0 frequency by twice the frequency resolution. And this is another important point, because if we don't have enough coverage, then we can definitely expect that the resolution or that the periodogram might find the wrong periodicity. And this is even considering for a case that the sinusoids have no white noise added into it. So that's what you see in the middle plot, the long scroll periodogram, and the bottom plot shows another case that we were studying, that we were analyzing, which is the Bayesian long scroll periodogram, which is another variation of the previous one, but that actually uses a Bayesian approach to try and feed a single frequency, a single sinusoid to your data. This is also applicable to some of the data sets that I looked at. So these are some archival data sets. I applied it for Kepler, a variable star that was observed by Kepler with the Kepler light curves. This is from a paper that was looking for differential rotation in some of these Kepler stars. And a similar case happens as the one that I showed in the first example, where you have a periodicity that is associated with the rotation period of the star. And then you have another peak in the periodogram that they reported as being the differential rotation, but it is really close to the original period, to the point that it's even separated less than one frequency resolution from the original rotation period, which means that it is possible that even though what you see in the top, it's the original periodogram, and the one at the bottom, it's a periodogram after you subtract a sinusoid with the frequency of the rotation period, you still find this period. And it's possible that simply fitting the period, the original rotation period, is not enough to just get rid of this artifact. There's the other case that I looked at, which is the case of Barnard star, also a well-known star in the variable velocity community. In this case, it is to illustrate the second example that I showed before for the total time baseline, where for this star, we can see that the variations over long periods of time tell us that there's a long-term activity cycle, similar to the one that we observed for the sun. The issue is that the periodicity is not resolvable. So similar to the previous time baseline, we don't have enough coverage to determine what is the true period of the long-term activity cycle. And there's been previous times in the literature that's been reported as a certain value. I cannot remember at the moment. But what we tried to do was, instead of trying to fit a sinusoid to the data, we tried to use a polynomial fit, a third-degree polynomial fit. And we actually found that in this case, the third-degree polynomial was actually better at fitting the long-term activity cycle than the sinusoidal fit. And it was even better at getting rid of some of the power at the low frequencies. Okay, for the last time of the talk, I'll go into how do we go about separating stellar activity from a rare velocity data. And as you will probably notice from the previous slides, there's a lot of focus on the frequency domain, because in the frequency domain, it is one of the most used methods in the rare velocity community. So that's why we focus a lot on that area. And in particularly, the method that I'll be discussing is called the magnitude square coherence. This is from also some work that I was involved at the beginning of my PhD that was published in 2022. The idea of this method is that on top of having a rare velocity time series, we also have another time series that is called an activity indicator, where an activity indicator, it's also taken from the spectra that we calculate the rare velocities. But in this case, we were interested in calculating how much of the variation of the star changes over time. So these are calculated, for example, one of them is called the S index, that it calculates the variation from the calcium H and K lines, that looks at the emission in these lines and determines how much activity happens at the chromospheric on the chromosphere of the star. And this time series tells information about how is the variation over time of the stellar activity. So with this idea, we have our rare velocity time series, and we have our activity indicator time series. We expect that the rare velocity time series has a planet signal and possibly other stellar activity signals. In this case, let's assume a rotation period. For the case of the stellar activity indicator, we're going to have only stellar activity signals. So we do not expect to see any planet signals in the stellar activity, in the activity indicators. So for this case, we imagine that we have these two time series. They have one shared periodicity, being the rotation of the star. A common way to look for correlation in between activity and RVs is to plot them against each other, which will represent the data, the plot in the middle. But the issue is if they're not in phase, so if they have a phase offset with each other, you might not see any correlation whatsoever. So plotting them against each other, you would normally try to expect to see a linear correlation, see a straight line, but unfortunately, there's a lot of cases you might not actually even see that. But what we looked at is to actually look at a different quantity, which is the one at the bottom, and that is the cross correlation, where the cross correlation is kind of a similar product as doing the convolution in between two functions. And the cross correlation, what we observe is that we can actually see an oscillation. And this oscillation tells us that there's a shared oscillation between these two time series. Now we use kind of the same approach of taking our Fourier methods and apply this to the cross correlation. So then we can obtain something that looks kind of similar to a periodogram, which is called the magnitude square coherence. This value goes between 0 and 1, where 1 tells you that there's a strong coherence in between these two functions, and it will tell you how strong is the coherence at different frequencies. So in this case, this peak in the coherence tells us that there's a shared periodicity at approximately, I believe, 0.01 for the case of these two time series, which is a rotation period that we injected into this synthetic time series. But at the same time, this coherence will not pick any planet signals, because a planet signal would only appear on the rare velocities. It will not appear on the activity indicators. With this in mind, then I go into the case study that I've been working on not only applying this method, but also on other methods that are meant to try to model the stellar activity from the rare velocities. So I've been working on 83 on the system 83 Leones. This particular system is made up of two sun-like stars, 83 Leo A being the main component, that has a similar mass to our sun. It has a mass of 0.95 solar masses. It is also known to be a very strong or a very active star. So we see in the rare velocities that it has a very strong magnetic cycle that shows in the rare velocities and also the activity indicator S index. So far, there hasn't been any exoplanets found around the star, and it's been surveyed by multiple times, by multiple surveys, by RB surveys. The companion, 83 Leo b, it's a little bit smaller, so it's a K2 type star with a mass of 0.85 solar masses. And this one has had 2 planet detections so far. The first planet detection came back in 2005 by Marcy et al. And this planet has a period of 17.05 days, while the most recent planet detection happened just last year by Salpor et al. In 2023. They reported a new planet with a period of approximately 95 days. The other important thing to mention about this case is that these are visual binaries. Their predicted separation is approximately 500 AU. So you would expect that the rate velocity induced by its companion, it can be mostly neglected from trying to look for exoplanets. So because of their separation, the gravitational attraction that they exert on each other, it is minimal, or it is much less than the one that we expect to find from any planets around each of the stars. Okay. So first of all, we also want to understand what's the data that we're working with. So we're working on some archival data for both of these stars. In particularly, I was working with the observation from HIRS at the Keck telescope, which is just nearby, and I actually got to see it yesterday when we went to the summit. One of the things that we also were interested in investigating is that these observations were analyzed by 2 different teams, or they were processed by 2 different teams. One of them was the Lee Carnegie survey, and the other one is a California Legacy survey. These 2 observations were the same, except for the California Legacy survey that took newer observations back in 2000, from 2017 to 2021. But the difference in between these 2 surveys is that they use different methods to process the variable velocities. In particular, the Lee Carnegie survey, they accounted for the systematic of the upgrade to HIRS that happened in 2004. So they determined that there was an offset after the instrument was upgraded. And then there was also a nightly shift, nightly zero mean shift. So they corrected for that when they published the variable velocities. Well, the case for the California Legacy survey, instead of, they just publish the variable velocity without accounting for the systematics, and they just include them in their modeling for the planets. So they just include an offset as one of their free parameters for the planet fitting. So this image, this graph shows the variable velocity for the case of 83 Leo A, and it compares the two observations from the California Legacy survey and the Lee Carnegie survey, where the blue data point shows the HIRS data before the upgrade, and the yellow one show after the upgrade. For the case of the California Legacy survey data, you not only have data from HIRS, but you also have data from the automated planet finder. And the observations look mostly the same for the case of the one between the California Legacy survey and the Lee Carnegie. There's only some variations in their values when they were calculated later on by the CLS team. Another important thing to take into account from these observations is that there is a spectral window artifact that is caused by the synodic period of the moon. What I mean by this is that most of the observations that were taken with Keck, with HIRS, were taken during bright time. So because you don't need as a dark sky to do variable velocities, especially for these stars that are particularly fairly close to us, so they're very bright in the night sky. You can have observations mostly taken during bright time, where bright time means that it's during full moon. So these graphs shows the phase of the moon and the number of observations taken, where if you're in between a phase of 0 and 1, that means that you're at full moon. And what you see is that most of them fall under this category, under this range, where we have observations mostly taken during full moon. The issue with this is that you basically created your window function that I discussed before, creates an artifact in your periodogram that lands at the synodic period, which is at approximately 29.85 days, if I'm not mistaken. So this vector window is just taking the periodogram of the observations, so of the periodogram of the window function, and what you see is that there's a high peak at almost a month at the synodic period of the moon. And this is particularly important because we have to be aware about this, because we find this peak, we find this peak in the periodogram, and we have to be careful that this cannot be characterized as a planet or as an stellar activity signal, but this is just solely caused because of the sampling of our observations. Okay. So now I go into how do we go about modeling the activity of 83 Leo A. For this star, the only work or the surveys that have looked at this star, they have only pointed out the long-term activity cycle of the star, but there hasn't been any particular modeling of trying to model the activity or to look for planets. So in our case, first we start by looking at what are the signals that we find in our data for this star. What we find is the same as had been found before. We find a very strong period at approximately 2,000 days in both data sets that we associate with the long-term activity cycle of the star. Then we also have a significant period at approximately 30 days that if we didn't know about the spectral window artifact, we might think that it's something real, but because of what we checked before, we know that this is caused because of the synodic period of the moon. With that, we take our observations, and another common method using radial velocities to try to model for stellar activity, it's done by using Gaussian processes, where a Gaussian process model, what does is to pick a function, a kernel, that's as it's known, and then you fit this model to the covariance matrix of your data. This model is normally physically motivated. So normally what it's done is to try and do a fitting of a quasi-periodic function. A quasi-periodic function is because we expect a stellar activity to be quasi-periodic, where we have a periodicity of the rotation, for example, or the long-term activity cycle, but we know that it might act like a damped oscillator, where you have a damping, you have a decay of your signal. So we use this approach for the case of trying to fit our radial velocities and our activity indicator S-index. And the graph that you see on the bottom, it's for the case of the radial velocity data and the S-index data, where the blue line shows some of the posterior samples of the distribution after we optimize our model and we use a Monte Carlo simulation to look for the best fit parameters. And we see how the GP does a good job at explaining the variability of this. From this, we can then extract some of the parameters for the case of the long-term activity cycle. In particular, we can detect and we can report what is the period, for the long-term activity cycle, where we find the period to be at approximately 2,200 days. And the other good thing that we find is that the results are fairly consistent using both data sets, using both the California Legacy Survey and the Lee Carnegie Survey. The other interesting thing that we were looking for, it's after we subtract the activity, the signal from the activity, we want to see if there are any remaining periodicities in it. So we want to see if there's either a planet signal or if we can detect any other stellar activity signal. And what we find is that in the residuals of the data, we find a remaining period at approximately 25 days, which after using our magnitude square coherence method mentioned before, by looking at the coherence between the residuals of the RBs and the S-index, we see that, 23 days, we see that this period is possibly associated with stellar activity 2 because it has high coherence between the RBs and the S-index. Lastly, I'll go over the work that I've been done so far on 83 Leo B, in particular this new planet detection at 95 days. So in order to find the 95-day period for 83 Leo B, first we have to make sure that we get rid of the signal from planet B. So that's the first thing that we have to do for the RBs, is to just take the parameters that have been found for the orbit for planet B and subtract them from the radial velocities. So the top plot shows the phase observations over the period of planet B with the model. And then at the bottom is the periodogram of the residuals. So after we subtract the signal from planet B, we look at the periodogram of the residuals, and we do end up finding this 95.4-day period that was supported in the Southport paper. And we find this period in both the California Legacy Survey and the Lee Carnegie Survey data. The next thing to do is to look at the coherence between the RBs and the S-index. to look for stellar activity signals, and particularly to confirm that this 95-day period is not caused by an activity signal. And that's particularly what we find when we looked at the 95.4-day period. There doesn't seem to be any strong peaks at that frequency, which indicate that this signal is not caused by stellar activity. But we do find some very strong peak at 18 days, which until now is still unclear as to what that might be associated with. So that one is kind of still up in the air. The next thing that we were looking at, and to compare with the previous result from Sarpo et al., was to look at the rotation period from the star. So the rotation period for the star over all the years in the literature that has been surveyed has reported that the rotation period lands in between 40 to 45 days. And the newest result from Sarpo et al. Reports that the period is at 42 days. One of the experiments that we run into that is looking for a pseudo window artifact is that, as I mentioned before, we have that the window function creates spurious artifacts in the periodogram. But not only that, having a periodic signal at a certain frequency can also create another spurious peak, and that's what we call a pseudo window artifact. So to look at the pseudo window, we basically take our observations and we inject a sinusoid into them. We inject, in this case, a sinusoid with the period of planet B. What we find from our results, which are shown in the periodogram on the right, it's that we looked at the periodogram for different phases of the sinusoid, on phases between 0, pi over 2, pi, and 3 pi over 4. And we find that there's this peak at 40.4 days that is significant also about the 0.1% false alarm threshold, and that is solely caused because of having a periodicity at 17 days. And we believe that the period that has been reported multiple times as being the rotation period, in particular, it's not actually the rotation period, but it's actually a pseudo window artifact. It is an artifact of just our sampling of the observations combined with having planet B at a period of 17 days. With that in mind, one of the changes that we did to the planet C model compared to the one from Sarpo et al. Was that Sarpo et al. Did the 2-planet model for H9 and 492, but they also did a GP model using the rotation period of the star, similar to what we did in the case for LE3 Leo A. However, because we believe that the rotation period is a false positive, it is a spurious peak, instead of using the rotation period that was reported by Starport, we used the period of the long-term activity cycle, which is a period of approximately 3,000 days. And what we obtain in our results is that for the case of planet B, we see that basically everything remains unchanged. We find the same period, we find the same semi-amplitude, but for the case of planet C, we do find a big difference. We find that the orbit is much more eccentric than was reported previously. The orbit that was reported by Sarpo et al. Was very close to a circular orbit, while the orbit that we find from our model, it's more of an orbit that has an eccentricity of 0.2. Besides that, the period and the semi-amplitude remain fairly the same. With that, I will give the summary for this case, where, first of all, we want to really emphasize how important it is to look for the artifacts of the pseudo windows of our of the sampling of our observations, in particular because this time we believe that the rotation period is actually an artifact, it's a pseudo window artifact. We also see that our GP model, in this case, might be preferred because of this reason to use a long-term activity cycle period rather than to use the rotation period that has been quoted multiple times in the literature. And we find that this updated 2-planet model and activity model is also consistent in both datasets. In both the Lee Carnegie and the California Legacy Survey, we find that planet B remains mostly unchanged, while the case for planet C, we find a higher eccentricity in both datasets. With that, I'll go into the last bit of the talk, which will be the closing remarks. As I mentioned, these are some of the main takeaways that I would like to take from this talk. I will say that RBs will continue to be a very important part of the future of exoplanet science. We know there's still a lot of work to be done, but we know that there's particularly a very bright future in this case. I mentioned how stellar activity still poses a great challenge in finding Earth-like analogs for radial velocities. And it is truly one of the main focus of the radial velocity community to look into ways that we can mitigate this stellar activity. We also noticed, and I also showed, how the spurious peaks caused by our observation sampling can masquerade as real signals and be particularly problematic if we're not cautious enough. And I think in particularly that the future for RV searches, it's very bright because of the new instruments that are coming up, where to mention just some of them, we have Express, Espresso, Maroon X, which is right here organized by Gemini, and also Newit, that can deliver precisions that are below 1 meter per second, which is what we need to find Earth-like analogs with amplitudes of 10 centimeters per second. But the problem then becomes is to really making progress as to how do we explain stellar activity. Thank you.
Well, thank you for the wonderful talk, Victor. Do we have questions?
How long do large star spots last?
Sorry?
How long do large star spots actually last?
Lodge?
Large star spots. You talked about star spots earlier.
Oh, star spots. Sorry. That depends. The variations normally will be attributed in between months to like a few months on the order of maybe 30 to 60 days. But what is also particularly hard about that is because you can have groups of spots that come in and out of view. So it will also depend as to if it comes in and out of view, then you might have the spots that are visible, and then if they come back out of view, they might still be there or they might not be there. So that's why it's another kind of particularly challenging part of it, because it will be a quasi-periodic signal on that end.
And presumably, I mean, maybe you filter by spectral type and luminosity class, but I guess irregular circumstellar dust clouds could give you similar hints of problems, right?
Yeah, exactly. So it's definitely something that depends a lot also on the spectral type, like you mentioned. For the case of M dwarf, we expect that the long-term cycles are particularly very different than for the case of sun-like stars. And same thing with the presence of spots on the terms of the timescales that they last.
So do you filter your studies by spectral type and luminosity class?
It is a particularly very important study in that end to really know also your star, because that also tells you a lot of what you can expect. In terms of sun-like stars, you really are looking for, especially rotation periods are on that order, that unfortunately are like approximately like on the orders of months, between 30, 20 days or 40 days. Well, in the case for M dwarfs, you can kind of expect that the rotation period will be a lot longer. So for the case of M dwarfs, you expect to look at rotation periods on the order of maybe 100 days or so.
Yeah. Thank you.
Yeah.
Do we have any more questions?
I think there's in the chat too.
There's one in the chat?
Or I don't know.
It's just me typing.
Oh, okay, sorry. Yes.
Actually, this is more a curiosity. We probably know the answer to that webinar. That STSCI is making the new attempt to detect atmosphere in planets and everything. They're going to put like several hundred hours of JWST and HST to actually try to directly detect atmosphere of planets.
Oh, okay.
Maybe you're not familiar with that, but I was wondering if there is any way to how these planets have been selected, or what's the main reason for this, or what is the best guess?
Well, what is the best case for how the HLVO planets were selected?
Yeah, it's the same question.
Okay. Yeah. So from what I read in the case of the document that was released, you have to look in particularly for multiple cases. One of them being how bright the star is, how close it is, because you want to make sure that you're looking at targets that are particularly ideal for HLVO, that are not too far, but also that are not too close, so that you cannot saturate the detector. And in particularly, I remember that there was a lot of focus on actually looking for sun-like stars. So most of the possible targets are actually F, J, and K type stars on that regard. In terms of the instrumental part of it, I'm not 100% sure on that part, but that's like, yeah, one of the main selection criterion that I can remember.
Okay, thank you.
Do you have like any other data that you can look into and see if you can disentangle and find more false positives?
Yeah, that is also, yeah, thank you for actually mentioning that, because another big focus that has been going on too, and that's also a lot of efforts that are happening now, is that a lot of these RBs instruments have also taken data from the sun. And that's a new project that has been ongoing also in the past, like maybe 5 to 6 years, which is the project of the sun as a star, where you are taking data, you're taking RBs from the sun, and you're trying to see how do you explain the solar activity from the sun, which is the one that we actually can know more or less the ground truth for the case that we have so much observation from the sun. So that is another effort that I've been working with in terms of Express. So Express has also been taking RBs from the sun, and we've been looking at how to deal with that case. In particularly, one of the major problems in that case is not only the activity signals from the sun of how strong they are, but also just the observations that are taken every day. So you have a very strong artifact in the window function from the one day, because the observations are taken every single day. And you can really see that very clearly in the periodic count.
I have a very basic question. Do we really understand the solar activity, like, in terms of we do? Okay.
No, we definitely don't understand the solar activity whatsoever and how to explain it. And that's why I think that was another, like, one of the main ideas is to look at the sun, because we have so much data on the sun, we can really like correlate 1-to-1. Like if we take our RBs from the sun, we have another ways to look at what was happening at the sun at the same time. So we have all this information from hydroseismology, for example, or information from all the telescopes that are just meant to observe the sun. But yeah, I would say that not even the one from the sun will be able to explain, because once again, it's a little bit of a mixture of a lot of stochastic processes combined with periodic processes that are really, really hard to predict.
Okay. Thank you.
Yeah.
Do we have any questions online? If you have questions, please unmute yourself and ask right away. Maybe we are good, I guess. All right, well, looks like we don't have any questions, so thank you so much for the talk.
Thank you.
Thank you for being here, so. All right.
Thanks so much.
Okay.